And I'm going. Okay, so back to topology. So the genus, again, is the number of holes. It's a topological invariant, which mathematicians have defined using an integral over the local curvature. So from this GIF here, you can see a mug would be topologically equivalent to a torus, as they both have one hole, or a genus of one. So this concept can be taken over to physics. And basically, we can consider wave functions which span a Hilbert space with a non-trivial topology. Or in other words, we view wave functions as a mapping from K-space to a manifold in the Hilbert space. And again, topological invariants can be defined which classify materials. So these can be integer numbers or a quantization that doesn't change under a smooth adiabatic deformation of the Hamiltonian. Some examples of that would be the Z2 index for topological insulators and the TKNN invariant. Trying to get to the next slide here. Oh, okay. So topological insulators, many of you may have heard of. They've been experimentally realized in 2 and 3 dimensions, but they were, of course, first predicted theoretically. The interesting thing about these materials is they have insulating states in the bulk. So they have a gap in between the valence band and the conduction band. These topologically protected gapped states in the bulk produce metallic surface states. So basically, the result of having a non-trivial topology in the bulk, when you come to interface with a trivial insulator, the topology cannot change unless the gap closes. They call that the bulk boundary correspondence. And another interesting aspect of these materials is that they have spin momentum locking. So on this diagram down here is basically a diagram of the 2-dimensional topological insulator. And equivalently, when you have an insulating bulk, it would be the interior of the 2-dimensional insulator, and the edges would be metallically conducting. And you can see here the spins are correlated with their momentum, which is very useful for potential applications in spintronics. Here, so, let's do that. So a Weyl semimetal. A Weyl semimetal basically is material that has special band crossings, which result in Weyl nodes. So for those of you who are not familiar, the Dirac Hamiltonian can describe relativistic particles. When you set the mass equal to 0, these Dirac spinors can be decoupled into 2 Weyl spinors with defined chirality. And so basically you can have materials with these protected band crossings based upon symmetry. And there's also materials with accidental band crossings, which are not protected from symmetry. And the recipe is you basically need 2 singly degenerate bands which disperse linearly through K-space with a well-defined chirality. And some examples are tantalum arsenide and tungsten ditelluride. A Dirac semimetal is very similar. The main difference is the degeneracy. So a Dirac semimetal can be viewed as a Dirac point can be viewed as 2 Weyl points of opposite chirality coexisting. So you have the 2 doubly degenerate bands cross with the 3D linear dispersion at a Dirac node.
Excuse me.
Yeah.
Could you explain these diagrams? What are these axes and what does those figures mean?
Yes. So the horizontal axes are the momentum, or the K-space, and the vertical are energy. So it's basically a dispersion graph. When you break inversion symmetry or time reversal symmetry, you result in a Weyl semimetal. The reason they have two cones as opposed to one is I believe it's called the Fermi doubling theorem, or the fermion doubling theorem, requires that these Weyl points come in pairs of opposite chirality. So it's just showing basically a general picture of what the dispersion would look like for a Dirac material. And these points are only found at specific spots in the band structure or in momentum space. Let me continue. For some reason, oh, there we go. Make sure I didn't skip one. Yeah. Okay, so some of the transport properties of topological semimetals. They have a non-trivial Berry phase, which you can detect experimentally. I'll explain more what that is. You get a very large magnetoresistance, which means the resistance under applied field becomes very large. Super high, or they call it ultra mobility, is a result of the small effective mass. And then we also see chiral anomaly, which is a negative magnetoresistance, which results from a parallel magnetic and electric field applied to a material. So the Berry phase, we would consider a Hamiltonian with a vector parameter r. And under the Adiabatic Theorem, it basically says if you start a system out in the nth eigenstate of an initial Hamiltonian, it will evolve as the nth eigenstate of the time-dependent Hamiltonian times a phase factor. And this phase factor can be calculated. You would put this back into the time-dependent Schrodinger equation and solve the differential equation. And you're left with two terms, a dynamical phase factor and the Berry phase, which is a geometric phase. And it's under a closed loop in parameter space. That part is important. And one can define what they call a Berry connection, which is analogous to a magnetic vector potential. And the Berry phase would be the integral of this Berry connection over a closed contour. Let's see here. So that was just a bit of background, and now I'm going to try to get through the rest of the paper. So platinum bismuth 2 has a Pyrite type face-centered cubic. That's what FCC structure stands for. And it does not have inversion symmetry, which means that, yes, XYZ is distinguishable from the negative XYZ. You can see from this picture, one of the crystals they grew had a very well-developed facet on the 111 plane. Now that's a certain plane in the Brillouin zone. For those of not familiar with that. Anyways, so the diffraction diagram here, basically they pointed their diffractometer directly at this plane. Sorry, the beam of X-rays directly at this plane, and were able to confirm that it was oriented along the 111. Oh, and all transport measurements were taken across this face. Let's see. So the resistivity, you can see here it's got a metallic behavior. It basically falls off to 0. At low temperatures, it follows the Fermi liquid T² dependence. It's got a very small rho naught, which is the residual resistivity. I think it was like 18 nanoohms centimeters. And this RRR, which is if you take the value of the resistance at room temperature and divide it by the low temperature resistance, you get a very large number, which means it's a high quality metal, not a lot of impurities. when a field is applied, interesting behavior arises. So we see a field-induced metal insulator transition. So we have this activation behavior appear with the appliance of a field. This has been observed in a lot of Dirac and Weil semimetals. It's very common. The extremely large magnetoresistance is also common in these type of materials. So this material, I think, was one of the largest ever reported in terms of the MR percent. 1 times 10 to the 7th is a pretty large number. You could probably think of a way that would be useful in circuits. Just by applying a field, you completely change the resistive behavior. So the magnetoresistance is quadratic in the low fields, which is expected from Lorentzian magnetoresistance. And then above 14 Tesla, a linear dependence starts to appear, which has also been found in a lot of these Dirac and Weil semimetals. I don't think there's any theory for that yet, though, that I've seen. Oh, and we see these squiggles, which are Shubnikov-de Haas oscillations, which are actually very useful in characterizing a topological material. So the Shubnikov-de Haas oscillations, they basically result from Landau quantization when a material is in a magnetic field. This expression is actually just the simplified two-dimensional expression. But you can see it's dependent on the cyclotron frequency, which is proportional to field. So as the field is raised, these Landau levels are more widely spaced. And that basically causes the density of states to periodically modulate with field. This scattering, so in relation to conductivity, scattering probability, which is usually proportional to the number of available states that electrons can be scattered into, which that would tell you that the conductivity gets modulated as the density of states gets modulated. And in fact, it happens as a function of 1 over field. In 3 dimensions, you have the KZ is non-quantized. So the same direction as the field is not quantized, so you get these Landau tubes. Anyways, just wanted to remind people of that if they were, I don't know if everyone has learned about that yet. So Shubnikov-de Haas oscillation. So this is, this graph is the oscillations after they have subtracted a third order polynomial background. I believe the colors are different temperatures. I'm not sure. I had to cut up these graphs, so all the markings might not be on there. But you see the oscillations decrease with temperature as expected. And from these oscillations, you can take a fast Fourier transform. They found 2 principal frequencies, 250 Tesla and 850 Tesla. And that basically corresponds to 2 different bands of the Fermi surface. And this Onsaga relation allows one to calculate the area enclosed in K-space by the electrons that are in the cyclotronic orbit on the Fermi surface. The fast Fourier transform, you will get these harmonics and as well as integer combinations of the harmonics of both bands. So that's kind of what these labels are, showing you what the peaks are. They also pointed out that in the higher fields, you will get this peak is split because of Zeeman effect, which will split an energy level. All right, under field. Let me see. I think that was all I had to say about this one. So further analysis of the Shubnikov-de Haas oscillations. they use the Lifshitz-Koshevich formula. This actually doesn't represent the entire formula. It is just the dependence of the oscillation amplitude. So they were able to basically take the oscillation amplitude at different temperatures and create this plot. And you can fit it using this equation to get the cyclotronic effective mass, this m star of each band. And you can also do what's called a Dingle Plot. So you're basically rearranging this equation so that when you fit a line to these points, the slope is the Dingle temperature, which is this TD right here. In the Dingle temperature, you can get the quantum relaxation time. And from that, you can calculate the quantum mobility, which characterize these bands as ultra-high mobility. So these numbers are generally large for a semi-metal. Let's see. So the non-trivial Berry phase. So the Shubnikov-de Haas oscillations, they follow a cosine function as a function of frequency over field plus this phase factor. This phase factor they don't actually digest in the paper. They kind of just put it there and say what the values mean from it. Here's what all the terms in the phase factor should be. The 1/2 was originally there from the Lifshitz-Koshevich formula. The Berry phase, which is this beta or related to beta, was originally not in the formula. And that is what we're after. So again, if you go around a closed loop in parameter space, you can acquire a Berry phase. And it's 2 pi times beta. And for a Dirac system with a linear dispersion, it has been theorized that you get a Berry phase of pi exactly. So if we were to solve for beta with gamma as pi, you get a 1/2 here. And basically that will cancel with this 1/2 and you're left with this other phase factor. The other phase factor they don't mention in the paper, or actually they might, but you get basically a plus or minus 1/2 from this phase factor for a 3D Fermi surface. 2D, it's equal to 0. And then there's also an additional phase. So these Dirac semimetals that have time reversal symmetry, the Berry phase is actually equal to 2 pi rather than pi, which causes this total phase to go to plus or minus 5/8. Let's see. So the anisotropy of the magnetoresistance, I'll quickly go over. So up here we have magnetoresistance percentage versus field in Tesla. And here they are sweeping the angle and taking these measurements. You can see that the oscillations are still there, although they have decreased in amplitude quite a bit. This is actually a polar plot. So they went in 360 degrees with this angle while taking resistance measurements. And it's got a twofold symmetric, rotation symmetric pattern. Let's see. And so they also did fast Fourier transforms of these oscillations. I don't know at what temperature, but I'm assuming a low temperature. And they plotted the amplitude values by angle. And from that, you can kind of infer the contour of the Fermi surface for these bands. The beta band, they basically said it was just a complex contour and anisotropic. And this alpha band, they tried 2 different fits, so a 2D Fermi surface fit, which fit the lower angles, but then kind of diverges, and this 3D ellipsoidal Fermi surface fit. which they agreed produced satisfactory fit, which also tends or agrees with their ab initio calculations, which I'll go over. So Hall resistivity. So these are the Hall resistivity. So if you are putting a magnetic field in the z direction and a current in the x direction, you want to know what the resistance would be resulting in the y direction. So as you lower the temperature, the slope of this increases, but we still have holes. Oh, sorry. So a positive slope means you have holes as the dominant character. A negative slope means you have electrons as the dominant carrier. So we have a positive slope through all the temperatures. But once you get to the lower temperatures, you get this slope change in the higher fields, which indicates multiband effects. So based on that, they fit the Hall resistivity to a two-band model. This NH and NE are the carrier concentrations of holes and electrons, respectively, and the mu H and mu E are the Hall mobilities of the holes and electrons. So the carrier concentration, you can see when you go below 20, nearly becomes equal by 2 Kelvin, and that is indicative electron hole compensation below 30 K. So one effect of that is you get a very large magnetoresistance. If you look in the equation, if these are equal, you basically get a non-saturating B squared. So I think a lot of that magnetoresistance comes from this electron hole compensation. Anywho, we also have a plot of the Hall mobility. You can see it is extremely small in the higher temperatures and then gets very large below 30 K, which is also consistent with the quantum mobility calculated earlier. So here are the ab initio density functional theory calculations. So this is basically what they would call the band structure. So they're plotting the dispersion along high symmetry lines. And so they found that there are 3 unequivalent pockets. The light hole pocket from the gamma to M line. So if you look on this here, the M is this edge right here. So they'd be referring to this yellow looking football guy. That's your light hole pocket. The heavy electron pocket is this guy right in the center of the Brillouin zone, which is the gamma point. And then your light electron pocket, which would be in the corners, and is represented by these purple, strangely shaped pockets. Over here, they're basically showing you a diagram. So this whole pocket would basically be this guy right here, right? So if you go from the gamma to M line, you're crossing this, which has a hole-like downward curvature. And this heavy electron pocket, which has less curvature, right, would be this guy right around the gamma point. This one, however, I'll actually show you the next slide, but you notice this looks like a Dirac cone, which is what they are claiming it is. So the Dirac point, which is down here, they calculated that it's at around 230 electron volts, which is fairly close to the value they calculated from the Shubnikov-de Haas oscillations. So you can get a Fermi energy from the information from those fits. So they are saying that this beta band corresponds to this Dirac point, and the alpha band corresponds to this whole pocket based upon the closeness of those two values. as well as the fact, if I go back one, you can, if you remember from here, the beta band has a very kind of strange contour as you rotate the angle. And the alpha band has kind of an ellipsoid dependence, which is consistent with these shapes. So that was kind of another piece of evidence that they relied on. So in review, I don't know what that's doing there, but we've seen extremely large magnetoresistance, greater than any report of these semimetals, a very large residual resistivity ratio, ultra high quantum mobility, as well as a high Hall mobility. Shubnikov-de-Haas oscillations, which revealed a non-trivial Berry phase. Oh, yes, I did forget to mention, sorry, that I didn't really explain this Landau level fan diagram, but basically you can take, you can plot, make a Landau level, to make this plot, you would get the, wait, sorry, I'm blanking out here. Yeah, the Landau level fan diagram, you would take the plots of the frequencies over field. Hold on here. Yeah, let me come back to that if there's any questions on that, but I kind of got off topic. But anyhow, the Landau level fan diagram reveals a non-trivial Berry phase, and the Hall effect, or the Hall measurements, revealed multiband characteristics from the slope change. And then we saw that the ab initio calculations are consistent with experimentation. And these are my references. And that is it.
Thank you very much, Matthew.
Yeah, no problem.
That was a very good presentation. I now hand over to Professor Benz, who will lead our discussions.
All right, let's just start with, does anyone have any questions they would like to ask Matthew?
Hello, Matthew. I have one or two things which I want to discuss, like something, if you can talk about. Like you were talking about chirality, which is you said it is well defined. So like when I read about chirality, it is like left-handed and right-handed. What do we mean by well-defined chirality? If you can just.
Let's see here.
Is the third point of this slide.
Yeah, so basically these dispersion graphs, they follow this Weyl Hamiltonian here. And you can see from the Hamiltonian you have this sigma dot p, which is basically your spinner dotted with your momentum. And so you basically have two separate components, and they'll couple with your spin, or they'll couple with a pseudo spin, which is a different degree of freedom depending on the system. But basically, along one of these bands, you'll only have like a spin up character, and along another one, you'll only have a spin down. So you do have, I don't actually have any good diagrams of it. Oh, I guess here, this shows kind of what I'm talking about. Or actually, this would be considered a well-defined chirality as well, except these exist in pairs. So here you would have a positive momentum electron, and it's always has an upspin, so that's why it's a chiral particle. And if you have this electron with a negative momentum has a downspin, so that would be considered a chiral particle. But these things aren't always spin. Sometimes they're pseudo-spin, which is basically it depends on the Hamiltonian. It depends on the situation. But yeah, that's as much as I understand it.
Okay, all right. This was helpful. If I can ask one more thing regarding this presentation. You talk about those oscillations, and you showed that graph where we had all those jiggly lines.
Yes.
And it had the information of temperature as well. I guess slide number 11 was the one.
Well, this one or the next?
Slide number 11, I guess.
11. I have a lot of like hidden slides in mine. Hold on.
Okay.
Is it this one? It's my 11.
It was the graph with all those lines and showing oscillations at different temperatures.
The raw data, the Shubnikov, the Haas.
Yeah, I think that's this guy.
The one before this, I think. Yeah.
Yes, this one.
Oh, sorry. Okay.
Yeah, so it seems that the oscillation are much more evident at low temperatures. So can you explain why this is the case, or if I'm reading it correctly?
Yeah, so at higher temperatures, you're going to have a lot of thermal energy, which basically you'll have a lot of your electrons in an excited state. So this, when you're at a lower state, you'll basically have all your particles, below or at the Fermi level, and so it's. The thermal smearing just makes the oscillations less evident, because so here when you increase the field and you'll have all of your electrons in a Landau level, which is below the Fermi level, and then as the field is raised up, the Landau level will go above the Fermi level, and all of those electrons will drop down into the lower energy state. So that's where you get your density of state modulation. I believe if you have a higher temperature, you're basically giving these particles more energy so that they're not going to drop to that lowest level. So I mean, this is generally with condensed matter physics. Everything interesting happens by the Fermi level, and so you need to get to low temperatures to observe that.
All right. Okay. Thanks a lot.
No problem.
Other questions? I've got one, Matthew. So I don't know that I really understand. So this large magnetoresistance is supposed to be a sign of the topological nature, but if you have these electron and holes that are compensated, you get a large magnetoresistance, whether or not you have topological materials. So I don't understand, is the topological nature making the electron and holes compensating each other, or is it just coincidence?
So right now, electron hole compensation is the only thought as to what is causing the large magnetoresistance. And I think it just so happens to coincide with these Dirac systems. Because a Dirac system, you need basically a Dirac cone with the Fermi level by the node. And so if your Fermi level is by a node where the conduction band, and if I can go back to... Yeah, if your Fermi level if these were touching, if the Fermi level was right here, right, you would expect maybe a perfect electron hole compensation. So I think I don't think it is necessarily an effect of the topological aspect of material, but that hasn't really been well thought out. I think the only thing people have noticed is that through these Hall measurements, you see a lot of the electron hole compensation. But if that were the only effect, you would expect a B squared, and there is not a B squared up into high fields. So that's why people think there may be scattering mechanisms that are suppressed until you put a field on the material because of this topological properties. But again, there hasn't really been much developed in the way of theory on that. But yeah, I don't think that, you can get electron hole compensation in trivial semimetals, and you'll see, that quadratic behavior continue. I think the linear behavior is more so indicative of the topological nature. My screen's kind of frozen here.